Alright, so we're going old school with these computer science PowerPoints. This is going to be computer science paper 1 revision. Um, since this is like one of the last days to study, I mean, we got the exam in like a few days, right? We also have a couple monkeys here for actually no reason at all. I don't know why I put those there. And these are going to be the topics that I'm going to be covering. Hopefully you saw that. Anyway, actually, no, I should probably give you guys a good look. Yeah, if you've already covered all these topics, then you probably won't learn anything new because I won't be going that in depth. I'm just going to be mainly like trying to speed run through this, like quickly skim through all this knowledge, right? And I wouldn't want to go in depth on all these because like some of these are like super boring. I'm not gonna lie. Anyway, let's just get into the first topic, which is the von Neumann, Harvard, and contemporary processor architecture. So the von Neumann architecture is basically just a CPU, and you've got buses two ways to memory, and this memory contains both instruction memory and data memory. Harvard architecture, on the other hand, is basically the same thing. The only difference is that the memory is split up into instruction memory and data memory, and we've got multiple buses now linked to the two different memories. Here's also a table of differences between von Neumann and Harvard architecture. To be honest though, you can sort of kind of like infer all of these just from like the definition of how both of them are different. Because, okay, well, okay, we ignore the first point because I don't think you'd put that in the exam. The second point is also literally like by definition, like how they are different. Like by definition, this is how they are different. Like the von Neumann architecture has one memory module for instruction and data memory, whereas Harvard has two different ones. Whoops. And then from there, you can infer that, okay, von Neumann would have a common bus for data and instructions because it's one memory module, right? And then Harvard would have separate ones. You can also infer that maybe it takes 2 clock cycles because first you need to fetch data and then you need to execute the instruction, so that maybe that's like 2 directions, whereas the Harvard architecture has 2 buses, right? So then you can maybe like fetch instructions and memory at the same time. And this fifth point is literally just the same thing, I'm pretty sure. Or the same idea at least. And the slow and fast is kind of, you can sort of infer from this clock cycle point. How I like to think about it is like maybe you can think of the buses as like streets, and then like you got vehicles transporting like data, information, stuff like that. And with Harvard architecture, you've got 2 streets, right? So you can transfer more stuff. And that's why it might be faster, but then at the same time, there's more maintenance cost. So Harvard architecture is more expensive. I don't know how accurate that analogy is, but that's how I like to think about it. Oh yeah, you also need to know about the contemporary CPUs, right? And how they differ to von Neumann architecture. Yeah, I mean, you can literally say anything here. Like, I'd be surprised if you somehow didn't get a point here. Just literally think of, like, the device you're using right now to watch this, and it's probably got some features that the von Neumann architecture doesn't have. I mean, that architecture is literally, like, I don't even know how old, but, like, it has to be so, like, too old, man. It's probably, like, outdated now, but I guess it's still important. Probably the best ones to memorize is just the 2 sets of memories, different buses, pipelining, and multiple cores. And maybe like onboard graphics as well. That's sort of interesting. Now on to CISC and RISC. So CISC just stands for Complex Instruction Set, and RISC stands for Reduced Instruction Set. This is of course talking about instruction sets for like assembly code, assembly language. And these are taught about like different CPU instruction sets, right? Because instruction sets are obviously linked to CPUs. So luckily, we actually had like a 9 or 12 marker on CISC and RISC in the June 2022 paper. This is the this is from the mark scheme. This is AO1, which is basically just random facts about CISC and RISC. So they say CISC is the traditional approach to processor design. There's lots of instructions available, although some instructions in CISC will rarely get used. I don't know how true that is, but I mean, they had it in the mark scheme, so I guess you can get a mark for that. RISC has a smaller number of instructions available, but several instructions can be combined to perform the same task as the CISC processes. I like to think about this with an example of, like, imagine you're trying to perform 5 times 5, right? A CISC complex instruction set might have the multiply operation, right? So then you could just do it in one line, so 5 times 5. But a reduced instruction set may not have the multiply operation, so you'd have to, instead of doing 5 times 5, you'd have to add 5 to itself 5 times, right? Like, so 5 plus 5, 5 times. And of course, a reduced instruction set is going to have the add operation. I mean, like, there's no way an instruction set is not going to have add. Like, I don't know what it would be able to even do without the add operation. So yeah, another point is CISC instructions are used regularly. CISC also has fewer transistors, less complex circuitry, whereas CISC has more integrated circuitry and is therefore more expensive and complicated. You can sort of infer that and logic it through. RISC instructions take only one cycle, whereas CISC may take several cycles. That also you can probably infer. RISC can only do complex things by combining multiple instructions, whereas CISC is done in one line. Again, that goes back to my example of the 5 times 5 and the 5 plus 5 plus, 5 times. Compilers for RISC need to be more complex than compilers for CISC. This might seem like a bit counterintuitive at first, because we're saying, okay, well, how is reduced instruction set more complex than the complex instruction set? But I mean, if you think about what the job of the compiler does, right, it's literally just like translating the source code, right? And because RISC uses more simple instructions, like there's less abstraction, right? You're gonna have more lines of code with the RISC instruction set, and that's gonna lead to more complex and longer forms of logic, right? When you're programming with the reduced instruction set, and so then the compiler needs to do more work. That's how I like to think about it, at least. Anyway, here's an exam question on CISC and RISC. Describe one difference between them. Most of these points we already said. Some instructions in CISC will rarely get used, while in RISC instructions are used regularly. And then also in assembly CISC, a statement takes one mnemonic, whereas it may take multiple mnemonics in RISC. This goes back to the 5 times 5 example again. That is actually a really good example. I don't know why. And I'm pretty sure a mnemonic is just like an operation, right? Like add and multiply, maybe. Maybe it's not exactly the same, but it does the job, I think. Then we got the point about the compilers. We also have complex circuitry point, and then CISC obviously has simple circuitry, and then that minimizes manufacture costs. Now we got interrupts and the interrupt service routine. So interrupts are signals generated by software or hardware to indicate to the processor that a process needs attention. Interrupts have different priorities, and how urgent they are must be taken into account by the operating system when allocating processor time. So how I like to think about this is, like, it's sort of like a firefighter. Like, they might be just doing like random stuff like eating food or something, until they get a call that some house like 2 kilometers away is on fire. They got to stop everything they're doing and then put all their attention onto that, right? And that's higher priority than whatever like he was doing before. And that's the same thing with how computers work. Like, maybe you're getting attacked by some virus. You're not going to be focusing on, you don't want the computer to be focusing on doing like some stupid calculations like 1 plus 1, right? You want it to like protect your computer from getting a virus. And that's where the operating system comes into play. It puts high priority on like this important thing, right? And then it interrupts the fetch, decode, execute cycle, and deals with the problem. The interrupt service routine, or ISR, is a special block of code associated with a specific interrupt condition. So this is like, going back to the firefighter example, this is kind of like the firefighters like code of conduct, right? Like this is the steps they have to do to ensure that the fire is like taken care of. And yeah, this is the ISR. The ISR takes some special procedures to like deal with whatever problem, like a specific problem that occurs. But yeah, you also need to know how stacks relate to the interrupt service handlers, which I think is the same thing as interrupt service routine. So yeah, describe how a stack is used when handling interrupts. You just say stacks use last in first out or first in last out. Literally the same thing. It's just different order. So stacks use those storage. Then, as processes are halted by an ISR, they are pushed onto the stack. When they are returned, they are popped from the top of the stack, so they are returned to incorrect order. Just any 2 points of those, and you get the 2 marks. Now onto BIOS. BIOS is firmware, and firmware is just software that provides low-level control of computing device hardware. It's firmware embedded on the motherboard inside the ROM, which initializes and tests the system, hardware components, and loads the operating system, OS, from a boot device. Basically, this is just all jargon for saying it's responsible for booting up your system. So describe what the effect would be of a computer having its BIOS overwritten. Well, if it's responsible for booting up the computer, then the computer would just not be able to boot up or load, or set up its initial configuration / hardware checks, making the computer unusable. You also need to know. It also says this in the mark scheme, like you need to know the steps that the BIOS goes through to start a computer. I mean, like, I've never seen a question on it, but like, I found a couple of steps that the BIOS takes to start up the computer. When you put the power on, the CPU looks for the BIOS, and then the BIOS gets initialized, starts all the hardware components like the CPU and memory. Then it performs diagnostic tests on hardware components, like basically just checking if everything's fine, making sure like you're not starting your computer with no power supply or something. Wait, no, that wouldn't work. You're making sure your computer doesn't start with like no storage device, maybe. Then it locates the boot device, loads the bootloader from the boot device, and then loads the operating system kernel into memory. And after that, well, we've loaded the operating system, we just hand over control to the operating system, because that's what the operating system does. Next, we've got the stages of compilation. The compilation process in computer programming involves translating high-level source code written by developers into machine code that can be executed by a computer. So the first stage of compilation is lexical analysis, and you input source code into it, right? And the output is tokens. So the purpose of this stage is the source code is read and divided into tokens, right? Which are the smallest units of meaningful data, such as keywords, operators, identifiers. This stage also removes white space and comments. On the right hand side, you can see the top line looks something like something a programmer might write, like source code. And then after he compiles it, that gets fed into the lexical analyzer, which turns everything into tokens. This stage also has something called the a symbol table, but I think I'll mention that later. So the second stage is the syntax analysis, which we input the tokens from the lexical analyzer, and we output a syntax tree. So the purpose of this is that the tokens are analyzed according to the rules of the programming language. Remember, all programming languages are different, right? And we gotta change source code to match the rules of that specific programming language. And then this stage ensures that the tokens form valid constructs. Like again, I'm pretty sure just making sure it meets the rules of the programming language, and it builds a syntax tree representing the hierarchical structure of the source code. The image on the right also shows like kind of an idea of what a syntax tree might look like. Then the third stage is the code generation. We input the syntax tree into there, and it outputs the assembly or the machine code. The syntax tree, oh yeah, by the way, parse tree, I'm pretty sure it's just the same as syntax tree. The syntax tree is translated into the machine code specific to the target processor, because like each processor has a different type of instruction set. And then this stage maps high-level constructs to actual hardware instructions, so I'm pretty sure like assembly code instructions. Then the last stage is optimization. We input whatever code we got from the code generation, and it just optimizes it. This, I mean, like optimization just improves performance and optimizes memory usage, right? So it's just good, I guess. Yeah, and here's an exam question on all the stages of compilation. I didn't talk about symbol tables, but just know that symbol tables are linked with lexical analysis, right? Anyway, you got 5 seconds to try this. 5, 4, 3, 2, 1. This is the answers. So in lexical analysis, comments and white spaces are removed, keywords are replaced with tokens, and the symbol table is created for variables. Syntax analysis builds an abstract syntax tree, that's kind of in the name, and then code generation creates the object code. That's also like sort of self-evident. Also, the purpose of code optimization is like pretty self-obvious as well. Like it just makes the code more efficient, makes the program run faster, and makes the program use less memory. Now on to linkers, loaders, and how they link with the stages of compilation. A linker is a computer program that just takes one or more machine code files generated by a compiler and then compiles them into one single executable program. A loader is part of the operating system that is responsible for loading programs and libraries. So here is an exam question saying, okay, some program is being compiled. Explain the process of compilation, including how code from the library becomes part of the finished program, justifying why each stage is necessary. So this was actually like, I don't know if it's like a 9 or 12 marker, but it was one of those long essay questions. So lucky for us, we can just look at the mark scheme and then steal the ideas. So AO1 is just the random knowledge facts. The compiler is effectively a group of programs. We talked about the stages of compilation before. And yeah, a linker is then used to combine the object code, which is the same as machine code, with the library code to make the final executable. Here's a bunch of like random information. We talked about like most of these things already, to be honest. So yeah, I'll probably just summarize this and go over stuff we haven't gone over. Some new things are, yeah, variables and subroutines are stored in the symbol table. And yeah, some other stuff is that code from the library is likely already compiled, and it might well have been written in a different language to the main program. That's pretty common. The main program source code will have contained lines importing the library code, and a program called a linker can incorporate the code from the library with the main program into a single executable file. Or there's an alternative approach, but this is mentioned in, well, I'll mention it soon after this. Evaluation, we've got lexical analysis is necessary to put the code into a format which can be read and processed by the syntax analyzer. Then syntax analysis is necessary to ensure the code is valid, just basically meeting the rules of the programming language. This guarantees that it will run. Code generation is necessary to turn the code into a format that the CPU can understand, like binary machine code, it's like ones and zeros. And then code optimization, they say while it's not necessary, does ensure the code runs quicker and uses less memory. They also say linking is necessary to ensure the library code is incorporated into the final program. And yeah, libraries are very important to programmers. Oh yeah, so this is the alternative approach that I was talking about. They talk about, okay, explain how linkers are used during the compilation process. They got 3 points. Links the main program to libraries. Then you have to say can either include them in the final executable code, or you can get the executable code to point to the external libraries. So this is basically just saying, okay, you can either have the library code or library stuff inside your code, or you can have your code point to the libraries. Now on to methodologies. Yeah, I'm not gonna lie, this topic like really sucks. I think you should just learn like the general idea of it. I mean, like if you want to learn the specifics, you can, but I feel like this topic is like just completely useless. Anyway, methodologies are a way to structure and formalize the software development process. I don't know like how often it's used in the industry though, whether or not it's used a lot or like not at all. I have a feeling though that literally nobody uses this, but maybe I'm wrong. What do I know? Anyway, the first methodology is the waterfall model. The waterfall model is basically just linear and sequential, which means that it just goes one way, right? So we go from requirements to design to development to testing, deployment, and then maintenance. If you want to memorize all that, you can, but I'm not gonna. I feel like after the exam, I'm just gonna forget all of this and never remember it ever again. You also need to know each phase must be completed before the next phase. That's what linear and sequential means. And it's also easy to understand and manage due to its rigid structure. An example of this might be like when you're developing software for a regulatory compliance system where the requirements are well understood and they're not likely to change, right? So like a bad thing about this is like you can't go backwards. So if you make a mistake in the previous one, that's kind of gonna mess you up for like the later stages. So you're really only gonna want to use this when you're sure that you're not gonna change anything in your design. Let's see. Some key characteristics. It's rigid linear progression. Each phase depends on the previous ones. So like I mentioned before, that's kind of a bad thing. And it's also minimal client interaction after requirements are gathered. The next methodology is agile. And agile is an iterative incremental approach that emphasizes flexibility and customer feedback. It's basically a loop, right? So we first plan, then we design, then we develop, then we test, then we deploy, and then I'm pretty sure you get like some customer feedback, see like how they like it, and then you adjust, like so it goes around in a circle until you've got your final product. It consists of small timed boxed iterations called sprints, usually lasting 2 to 4 weeks. But I mean, like I feel like that's just an arbitrary number. It can really depend on whatever company you're working at. Agile promotes adaptive planning, evolutionary development, and early delivery. A use case of this would be maybe when you're developing a web application for a startup where requirements are expected to evolve based on user feedback. Some key characteristics are it's flexible and adaptable. You can get continuous customer feedback because like you're always trying to test and then adjust, and it's like iterative with regular like updates and releases. The third one is extreme programming. This is a type of agile methodology that focuses on technical excellence and customer satisfaction. It emphasizes practices such as test-driven development, so you basically just continue testing and adjust. Pair programming, continuous integration, I have no idea what that is, and frequent releases. Extreme programming encourages regular communication with customers and team collaboration. And an example of this might be when you're developing a financial software application where high quality code and rapid response to changing requirements are critical. So this has a high emphasis on code quality and technical practices, and it also has frequent releases in short development cycles, and then the customer involvement is also very high in the development process. So yeah, this is very similar to the agile one. I think like the only differences I have here are like the code quality and technical practices. I'm sure like there's some more ones, but like I really didn't want to research more about methodologies, man. um, so yeah, we got spiral methodology. The spiral model combines the iterative development with systematic aspects of the waterfall model. So it involves repeated cycles or spirals of planning, risk analysis, engineering, and evaluation. Each spiral addresses potential risks and refines the project through multiple iterations. An example of this might be when you're developing a large-scale defense system where risk management and validation are crucial. This has a focus on risk assessment and management. It's iterative, like a spiral. I guess that's why it's called spiral, and it's very flexible in handling changes and evolving requirements. The last one is rapid application development. RAD emphasizes quick development and iteration of prototypes over rigorous planning and testing. So I guess this is kind of similar to the agile one. You basically just make a bunch of prototypes, you get feedback, and then you try and adjust, I guess. Do a bunch of testing, and then you implement the feedback. This might be a good use case for when you're making a mobile app where time to market is critical and user feedback can quickly shape the product. Some key characteristics are its rapid prototyping, frequent iterations, user involvement, and focus on quick delivery and iteration. So yeah, I mean like agile, extreme, and rapid are like basically the same, I feel like. Yeah. Here's a table if you want to use it. I mean like for this topic I'd literally just like skip it, to be honest. I'd rather lose the like however many marks they ask than answer these dumb questions, man. Anyway, modes of addressing memory. Thank you to 101computing.net. I didn't ask them for permission. I stole their content. It was too good not to steal though. Anyway, we've got immediate addressing, which means that the data with the data that is used is hard coded into the instruction itself. For example, when you add 7, nothing needs to be fetched from memory. The instruction means that the value 7 will be added to the value currently stored in the accumulator. This is the fastest method of addressing, as it does not involve fetching anything from the main memory at all. Pretty straightforward. You're just immediately accessing the value. Then we've got direct addressing, which is also very simple. It basically just fetches the memory location instead of the value, right? So, for example, add 7. In this case, it's not going to add the value 7. It's going to instead add the value currently stored at memory location 7. And this is what the Neumann computer uses. It uses direct addressing. Now we've got indirect addressing. This is basically similar to direct addressing, but we've got another step in the cycle. So we first look to memory location 4. In this case, if we want to load 4, we look to memory location 4, and then that memory location holds the address of where the value is stored. So yeah, the fetching a value is a two-step process. First, indirect address is used to locate an entry into a lookup table called a vector table, where the actual address of the value can be fetched from, where the actual address of where the value can be fetched from is stored. So yeah, hopefully this diagram illustrates how it works. I think it's pretty simple though. Next, we've got index addressing, which basically uses like offsets to find where the actual address is. So this address is probably ideal for storing like values in arrays, because arrays are often stored like in a complete block of memory, so that like sequential and consecutive, right? So in this example, I think they go to memory address 4, right? But then they have this little like subscript 2, which means they want to go to the next 2, I think, and that's the offset. The offset is 2. Yeah, anyway, hopefully that made sense. Alright, now we've got ACID, record locking, and referential integrity. So, I mean, luckily we just have an exam question on explain what is meant by referential integrity, so we can just steal their definition. This is talking about context in like some review website. But referential integrity just means that you're ensuring that changes are consistent across the database. So if a record is removed, all references to it are removed, and a foreign key value must have a corresponding primary key value in another table. Moving on to the ACID properties in database management systems, we've got atomicity, I think, however you pronounce it. This ensures that the entire transaction that takes place at once or doesn't happen at all. Then we've got consistency, isolation, and durability. You can read the other definitions, but how I like to think about this is for databases, it's really nice to think about it in terms of like banks, right? Because for the first one, a bank would need to ensure that like if you're transferring money through accounts, you need to make sure you transfer it like completely, or else like you just won't do it at all, right? To make sure that no money is lost through transactions. Then for consistency, you need to make sure that all the money you send or transfer between databases are consistent, right? Like you don't want some random person like somehow losing £1,000 or something randomly or something. Then for isolation, multiple transactions occur independently without interference. You got to make sure like, because like multiple people are using banks at once, right? You got to make sure, okay, like you're going to adjust this database in this one bank. You got to make sure that doesn't affect another one, so they're independent, right? Then for durability, the changes of a successful transaction occurs even if the system failure occurs. So like in the case of like two business deals happening, you got to make sure that transaction happens, right? And nothing is lost through transaction, even if a system failure occurs. Then we've got record locking, which is a technique. Well, actually, this is taken from Wikipedia, by the way. This is a technique of preventing simultaneous access to data in a database to prevent inconsistent results. So, I mean, this is kind of linked with the consistency in ACID. And a classic example is two bank clerks attempting to update the same bank account. So imagine like you got one bank clerk and you got another one. These guys look kind of weird, that's why I picked them. So yeah, imagine we're trying to give money to clerk 2, but at the same time, some random imposter is talking to clerk 1, and he is trying to adjust the like stuff in my bank account, I guess. So we need some sort of like consistency here, right? Because like, okay, if we can't both change like whatever is happening, because like if we didn't have record locking, then one person would change it, and then the second person would change it as well. Like then the second person gets priority, which doesn't make sense. We want both of these changes to occur. Or actually, we wouldn't want like some random imposter to do that. But like that was a bad example. Okay, imagine instead, you're talking to one clerk, you're trying to change something, and then you talk to another clerk after you finish talking to that guy, right? And then they both go do their computer stuff, like trying to change like the database. Like one clerk might overwrite the other clerk, is what I'm trying to say. A simple way to prevent this is to lock the file whenever a record is being modified by any user, and that's basically what record locking is. Then we've got DNS. There's actually an explanation by Amazon. They made like a 5-minute explanation of DNS, which was pretty good. You can watch that if you want. I'll probably leave a link in the description to it. But if you don't want to watch that, I can just summarize. Basically, DNS is the phone book of the internet. It's used to find the IP address corresponding to the URL from a website. So, yeah, this is a pretty good image. We've got our client, which is just whatever computer you're using, and you're trying to access a website, right? So for example, like we've got example.com, right? You send that to the DNS resolver, and actually we've got a root name server here, but like there's an exam question which doesn't really mention it, but I'm just gonna explain it how it should be explained. We send the URL to the DNS resolver, then the DNS resolver sends it to the root name server, which only knows about like these last parts, right? Which is like the roots. It only knows like .com, .org, or like .co.uk, stuff like that. And then it sends back, okay, given this root name server, or given this root name, we send back the name server. So like in this case, the example.com. We send the .com to root name server, and then it sends like example.com to DNS resolver, and then DNS resolver sends that to the TLD name server, which then I think sends the full URL to the DNS resolver, and then that sends it to the authoritative name server, which sends back the IP, and then the IP is sent back to the client. So yeah, this is a pretty long process, but this is only gonna be true for like random websites that nobody uses. Like I'm pretty sure if it's a popular website, like maybe like YouTube or Google, then the IP address is stored in the DNS resolver's cache, or like the other server's caches, right? Like cache is just like frequently used memory. So it just checks so like if someone was trying to like access YouTube, right, it wouldn't go through this long process. It'd probably just send it to the DNS resolver, and then DNS resolver would be like, oh, okay, this guy's trying to go to YouTube. Like everyone's trying to go to YouTube. Let's just we know the IP address. Let's just send it to the client. Hopefully that explanation was alright. Like if it wasn't satisfactory enough, you can go watch that video I mentioned. But here's an exam question. Explain how the DNS plays a role in websites being loaded. So yeah, here's what the mark scheme is saying. DNS is used to resolve IP corresponding to URL. Request sent to DNS resolver. It checks its cache. If it doesn't have it, it sends it to the TLD name server, and then the authoritative name server, and then the IP address is returned back to the requesting client, or an error if no resolution can be found. So interestingly, this doesn't really talk about the root name server, but yeah, I don't know. I feel like this mark scheme is not really that inclusive, you know? It doesn't really cover the whole picture. Anyway, we've got packet and circuit switching. So packet switching, packet and circuit switching are two different methods to send data across multiple devices. We actually have an exam question on what packet switching is, right? So in packet switching, data is split into chunks called packets, which have labels, including the address they're being sent to and the order. Each packet is sent onto the most convenient route, meaning they may arrive in a different order to which they are sent. Once the packets arrive at the receiver, they are reordered. Now, I didn't manage to find a circuit switching question from OCR, but this is from the Cambridge exam board, which is like sort of linked to OCR, I guess. But yeah, we're just gonna steal these guys as mark schemes. It's not as detailed, but I guess it's just a mark scheme. So yeah, circuit switching. A circuit is established at the start of communication. Oh yeah, also this is used in the context of a voice call. Yeah, a circuit is established between a sender and receiver. This lasts for the duration of the call, and then the link that makes up the circuit is removed. And lastly, we've got legislations, which is literally the worst topic ever. This is literally so boring. But I mean, like, you need to learn it. So yeah, I mean, if you look at the actual laws, like, they got like some more like specific stuff, but like, I think it's better to just learn like the general idea of what the law is. or the act, and then you can just like write random stuff, man. Like when you get a question, like a 9 mark question on this or a 12 mark question on this, it's literally it just turns into English language now. Like you need to write random stuff, you know. It turns into English paper. The first one is the Data Protection Act. I don't actually know if you need to know the year, but I put the year there. The Data Protection Act just basically protects, just gives protection for your own personal data and information. For example, like your bank details, obviously you want that to be protected. And this act also allows you to request a copy of the data held about you. So imagine like you're signed up to some website, right? You have the, like, the, what's the word? You have the right to ask like the company, like, okay, what data do you have on me? The next one is the Computer Misuse Act. This stops people from like misusing computers. So like imagine you found someone's password, you're not gonna start like, or apparently this act is gonna stop you from like transferring money. Anyway, we've got the Copyright Design and Patents Act. This one is like pretty obvious. I feel like you can just think about like movies and copyrighted music. The last one we've got is the Regulation of Investigatory Powers Act. This allows the Secret Service, which I don't know what they are, they can legally wiretrap online conversations in the interests of national security, provided that a warrant has been issued. And internet service providers and mobile phone companies, they have to give up information upon request from an authorized authority. So obviously not just any random person. And also you can also talk about how this act can be like used corruptly, I guess. Because if you have the power, like higher ups have the power to do like all this stuff, then you can speak about how like, okay, well, that's a breach of privacy or something, you know? Anyway, like, who cares about this topic? We can move on. Oh, actually, we've got nothing left. Yeah, so that's the end of it. Hopefully that was alright. And yeah, alright, goodbye.